In this video, we're going to be discussing cluster analysis. That is a method, well, a series of methods. We'll be focusing on one specifically, where we can group participants with similar characteristics together. So let's get started. All right, well, we're going to start this lecture set with a review of a couple of important concepts that will be needed when we're discussing cluster analysis. We're going to follow up with a little bit of context when this could be utilized, discuss the algorithm involved, and then focus on interpretation, which is actually a pretty difficult part of cluster analysis. After this, we're going to move into the details of some of the different options that we have. And finally, in a separate video, but as part of the same lecture set, we'll be discussing how to implement cluster analysis in software. So to start with, in our review, we're going to begin with standardization. So ultimately, standardization is a way in which we can rephrase particular numbers, or actually entire variables, to instead of being on its original scale, say we have miles or we have kilometers, maybe we have feet or yards or inches. These are all different scales that numbers can be on. Instead of being on those scales, we're going to change the scale to be standard deviations. So now the number 1, instead of representing 1 mile, will represent 1 standard deviation. This is actually a really useful thing when we're trying to combine information from different variables that could be on very different scales. So let's say I want to combine an individual's test score in one particular class with an individual's test score in another class, where the two professors grade very differently. The question comes up, well, if the two professors grade very differently, how can I combine these? And one of the methods by which we can combine these is by standardizing the variables first. Sometimes this is also called norm referenced, in that we are referencing the sample norms when we create these values. You can also represent population norms if you want to. But ultimately, that is one of the potential risks of this. In any case, it can be extraordinarily useful for combining values, and it's something that we do pretty often in a couple of the analyses that we'll talk about in this class. So there's a couple of different standardization functions. I think probably the most common, and in my view, we'll call it the most useful because it's the most common, is this one here. Usually you'll see a z equals before it, representing a z-score, and if you've ever wondered what a z-score actually means, a z-score just means the number of standard deviations, with a value of +1 meaning 1 standard deviation, a value of -1 also meaning 1 standard deviation, but in the opposite direction in reference to the mean. So here we take the individual data value, we subtract the mean, and then divide by the standard deviation, and that's how we get our standard score. With regards to distance, consider how you would normally think of the word distance. And what I mean by that is, if I asked you, what's the distance between 2 points, what is it that you think of? And you may think of like 2 points, like 2 dots on a graph or a chart, and you're calculating the distance between them. You might think of like 2 points on a map. You're a traveler, and so the distance between, my house and grandma's house or something like that. You might think of a residual. We talk about residual distances in statistics pretty often. And for all of these, you'd be right. These are all different distances. What you may not think about is that all of these are actually different kinds of distances. Within the graph, the distance between 2 points, that's a particular kind of distance. That's a straight line. In fact, we'll call that Euclidean distance, and we'll get into that in a moment. But that's a particular kind of distance. How does that differ from travel? Well, let's say you're traveling from here to, I don't know, Moscow or Beijing, somewhere on the other side of the globe, and consider how you're going to get there. And I bet you $1, it's not going to be in a straight line. In fact, in this case, you're going to have to travel around the globe. You're going to have to go in a circle. That particular type of distance is called spherical distance, where you have to travel around a sphere to get from one dot to the other. Even if you're just driving from here to the grocery store, think about the distance. If you put a dot on a map where your house is and a dot on a map where the grocery store is, the distance that you have to drive is not a straight line. Typically, you have to drive on like a road and then make a turn on another road and then make a turn on another road. And so that distance is a different kind of distance, that distance that you actually travel. In fact, if you're talking about going on square blocks, that is, if all of the roads you travel on are at perfect right angles to each other, that particular type of distance is called Manhattan distance, after the city Manhattan. Another distance you could think of with travel, not to beat a dead horse here, but is time. It's a weird travel distance, but if I think about how long does it take me to get to the grocery store, or if someone asks you, hey, how far away is blank, and your response isn't 157 miles, your response might be, it's about 2.5 hours away. Time is a measure of distance. So there's a lot of different kinds of distances that you every day interact with. And this is something that can come into play when we are using formulas that require a definition of distances. What type of distance do you want to use? And I think a great way to conceptualize at a elementary level what types of decisions we're making in the analyses we'll talk about in this lecture set is the decision as to whether or not, when somebody asks you how far away is something, you give them miles or you give them time. And I think if you think about that, maybe you just default to one, which is okay. But maybe within the context of the question, you know that one of those answers is going to be more useful. And so that's the distance metric you select to communicate. And within this context, and within every context where we make these kinds of decisions statistically, I think that that's how you want to approach it, is by thinking, what information do I want to communicate? And then just being really clear after the fact as to what information you ended up actually communicating. So again, I mentioned Euclidean distance. This is the distance between 2 points on like a graph or a chart. And it follows a very familiar formula. That is the Pythagorean theorem. Now, I want to be careful here. The Pythagorean theorem, a squared plus b squared equals c squared, is what's used for the distance, where a represents your horizontal distance, b represents your vertical distance, and c is the diagonal, that is the line that connects your 2 points. So c is actually the distance, but notice that this formula solves for c squared. So I'd have to, if I was trying to find a distance using this formula, take the square root of both sides. So on the right-hand side, I get c by itself, and on the left-hand side, I'd get the square root of a squared plus b squared, which is exactly how we find Euclidean distance between 2 points. Of course, a and b are no longer a and b because it involves 2 points, but this is the exact formula basis for how we calculate Euclidean distance. All right, well, now that we've got our background down, we can go on and look at the problem that we're going to be trying to solve in this class. So for cluster analysis, our goal tends to be to create groups. Why? When would this ever be useful? Well, consider if I had a marketing team who thinks that some customized materials for marketing might improve sales. In this particular context, I might have a team who could come up with 5 sets of customized materials, but maybe it's unreasonable to expect them to come up with a really good set of customized materials for every single customer. So what I want to do is I want to use statistics to identify some different marketing groups within my customer base. And that's a great place where I could use cluster analysis to identify clusters of potential clients who I can use targeted marketing with. Perhaps I want to use this to identify patterns. So let's say I'm a biologist looking to study species of some type of animal or plant. In this particular case, maybe I record characteristics of a bunch of plants or animals, and I look to see, is there a pattern that can be clearly identified within these variables? And if so, that would be a way in which I could use this cluster analysis to potentially help me identify a subspecies. In the video example that is used within this, and I say used within this, hopefully you've gone ahead and watched the video, and if not, I encourage you to do so. Efficient dating is the context in which that individual uses cluster analysis, and the presenter talks about how by creating clusters of dating profiles within the people that this person was trying to date, he was able to kind of target his profile to address those specific individuals. Now, one thing that I think is important to realize is with all of these, we have a goal outside of the cluster. Typically, our goal is to make the cluster and then to do something with it. So in the video example, we create groups of individuals, and then we use those groups to identify the particular questions I need to answer to customize my profile to be attractive to them. So typically, we're using cluster analysis to create groups for a purpose to use the groups. And we'll come back to that idea later. Big note within cluster analysis, and I say this because there's another analysis that does a very similar thing but with the opposite. A big note is that for cluster analysis, we group participants. We do not group the variables. So when we're looking at this, participants are who we're trying to create groups of. I'm trying to create clusters of participants so that I can group them together and use those groups for a particular purpose. And that's the goal of cluster analysis, is to find groups of participants. All right. Well, in place of equations or models, cluster analyses have steps or algorithms. And I don't want you to hear me that we can't represent this as an equation or as computer code. I mean, obviously we can represent it as computer code because we have to run it on the computer. But the better way to think about cluster analyses is as a series of steps that you walk through to get to your final solution. And that's a bit different than the way that we normally approach it. So these steps in this class, we'll call it an algorithm. And again, distinguish themselves from equations, which are also a series of steps simply expressed mathematically, in that we're literally going to write out the steps used for this. Now, it's important to recognize with cluster analysis, there's a bunch of options. And in this class, we're not going to talk through all the options. We're going to talk through some of them. In fact, we're going to really focus on one of them and then reference a few at the end so you can kind of get a feel for what the other options are and what they do. But I want to be really clear at the front that we are going to focus on one and that there's a lot more that we could use. So be aware of that. These different options that we have, I mean, people just don't make these for fun. I don't know, maybe they make them for fun. But the goal is to come up with, for a particular context, an option that balances between the fit accuracy, the assumptions that we make about the data, and the complexity of the algorithm itself and its interpretation. So ideally, we would have something that fits very well, that makes very few assumptions, and that isn't complex at all. But typically, as we increase the complexity, the fit gets better. As we have more assumptions, the fit gets better sometimes. As we have more assumptions, maybe the complexity can be reduced or increased depending on which assumptions we make. So all these do tend to go together in some kind of a balance. And the goal is to, for our particular situations, either find or from a statistical view, create the algorithm that best balances these. In this lecture set, we're going to focus on k-means clustering. And again, we'll briefly show a few others later. But the reason we focus on k-means clustering is it's one that is pretty good fit, it has pretty few assumptions, and it is extraordinarily not complex. So we're going to talk about the algorithm in a second, but it's understandable, I think. For this approach, we have to start with knowing the number of clusters, which is incidentally, it's probably its biggest limitation. But the number of clusters, we'll call it k, is something that we start with up front. So the k is the same k in k-means clustering, in that k is the number of clusters that we start with. After we have the number of clusters, pretty much we just plug in that number and let the algorithm do its work. And what it's going to give us is for each participant, it's going to let us know which cluster that participant fell into and which participants cluster with which other participants. And we can look at that at least in two variables in a graph. All right, so let's talk about the k-means algorithm specifically. The main reason I really like k-means is because the algorithm is very simple and straightforward. Ultimately, we randomly assign groups to data points. We then find the middle of each group, which is called the centroid. And by the middle, I mean that we take the mean of the x values in that group and the mean of the y values in that group. So let's say I'm doing two groups, k equal to 2. 2 means clustering, k equals 2. K means clustering with two groups. So I look at all the data points that were randomly assigned to group 1, and I find their mean x value, so that's the middle horizontally, and their mean y value, that's their middle vertically on two variables. And that's the middle of the group. And then I go to the second group and I do the same thing. Mean x value, mean y value, that's the middle. That's the point of the middle. Notice that I'm using the mean. This is k-means. I can use the median or the mode, and that gives me an algorithm called k-medians and k-modes. In fact, in the video example, the speaker used k-modes primarily because their data was categorical data. You can't take a mean with categorical data, so he used the mode of the data, which is a good way to figure out who has the most values within a categorical data set. After this, we assign each point a group based off where the centroid is closest. So now that I know where the middles of the group are that I found in step 2, now I look at all of the data points that are closest to the middle of that group. So let's say I have one group that's way over in the top left and one group that's way down in the bottom right. Well, all the data points in the top left, whether they were initially assigned to group 1 or group 2, are now going to be assigned to the centroid that's in the top left. Let's call it group 1. So all the data points that are closest to that middle of the group are now going to be classified as in that group, and vice versa. Down in the bottom right, all the data points that are in the closest to that centroid are going to be classified within that group. So each point is assigned a group based on where that centroid is closest. And now we repeat. So after we reassign the groups in step 3, each group is going to have a new middle. So we find the new middle, and then after the new middle is created, different data points might now be closer to different group middles. So we reassign data points to the group middle, and if different data points were assigned to the group middle, we then move the group middle, and we keep going over and over and over again. And that's it. We keep going until no groups change, and then we're done. And that's the k-means algorithm. It's not too bad. So this might, as I'm describing it verbally and as I'm trying to say top left and bottom right, it might seem a little abstract. So let's actually look at a visual example of this, and I think it might help. But do come back to this written out algorithm, because I think this is going to be helpful in conjunction with a visual example to really understand the details of what's going on. All right, so we start off with a data set. And then within this data set, we randomly assign each data point to a particular group. And in my visual example, I'm using red and green. So this was step 1. And I should note that it's step 1 in my process because I think it makes it a little bit more intuitive. But I could just as easily start with a different step 1, that is randomly assign the group middles, and then start at step 2. Now based in mine, I now have red dots and green dots, and so I'm going to find the average x value and the average y value for red, and that gives me the center red dot. I'm going to find the average x value and the average y value for green, and that gives me the center green dot. All right, so with this, you'll notice that in the red dot and the green dot actually, if you look to the green centroid, that is the bigger green dot in the image, to the bottom right of it, you'll see that there's a data point that's assigned to the red group, but is actually really close to the green quote-unquote middle. And so looking at this, what we would say is, that red point should probably be in the green group if the middle of the green group is where that green dot is, because it's closer to the green middle than the red middle. And so in that case, what we're going to do now is to use that logic with every single data point. For every single data point, we're going to ask, are you closer to the red middle or the green middle? And if it's closer to the red middle, we're going to set it to be red. And if it's closer to the green middle, we're going to set it to be green. And after we do that, what we see is that a lot of the data points change their group classification. Now, after that change, what we're going to end up doing is you can see the red centroid no longer looks like it's in the middle of all the red dots. It doesn't seem to be the group middle anymore, and that's because a lot of the dots that are now colored red were not colored red originally. So what we have to do is find the new middle for the new group classification. So we're going to do this for red and green, find the new middles. But now that we have new middles, some different dots are now closer to red and green. What I want you to notice, though, because it feels like this process may go on forever, is that now it's a lot fewer dots. So I might have a few dots that change at this stage, but certainly not half the data set like I had earlier. So here, again, I'm going to look at every dot, and I'm going to say, are you closer to red or are you closer to green? And if you're closer to the red middle, you're going to be colored red now. If you're close to the green middle, you're going to be colored green now. And that's going to change a few of my dots. And after that changes a few dots, again, now the middle moves again. And then I'm going to change the dots again. And then I'm going to move the middle again. And I'm going to keep going until I assign the data points to the groups. And when I do that, all of the red dots that were assigned to the red group were red in the last step too. That is, there's no changes, there's no updates to be made. And that means if I try to move my center, well, there's no change in that either because there's no new data points that have moved where the middle of the red group should be. And this is when I stop. There's no change from the last groupings. All right, well, this has been our introduction into K-means clustering. In the next videos, we're going to go further on into some interpretational characteristics and some of the options and details that we have within K-means.